Dear students, we talked about in the previous class about particle in a one-dimensional box, and I left you at a point particle in a one-dimensional box. We derived the relationship for the normalized wave function, which was root 2 by a sine n pi x upon a, and we derived the relationship for energy also, En, that was n square h square divided by 8 ma square, and we plotted this wave function for the different energy levels. For n is equal to 1, at all places the wave function is positive, and we plotted like this one. At n is equal to 2, we plotted like this one, where this part is positive, this part is negative, sign of the wave function. We plotted for n is equal to 3 like this one, where this is positive, this is negative, and again this is positive. And similarly we can plot for higher energy levels also. Okay, so we have three nodes: positive, negative, negative, positive, and again negative. Okay, so this way we can plot for n is equal to 4 also. And then I said you that these are the points where psi is equal to 0, and we say this to be equal to nodes. If you plot psi square, then all will be positive, all psi square will be positive value, and you get a curve like this one. For this, it is this one, not drawn to a scale, but it will be something like this one. It will touch this point, and then it will be plus plus. So there is no need to write the sign also, it's all positive, like this one. Sorry, it has gone. Let me make it a little more clear. Like this one. Okay, same way you can plot for the fourth state also, fourth quantum state also, where all is positive sign. So this is plot of psi square. And then I said you, and I left you at this point, that if you look at this point, the psi square is 0. Okay, so what you say? The probability is here also, but at this point, at one point, probability is 0. Okay, probability, actually not probability, we are plotting psi square, and psi square is probability density. So most often the question is that why does a particle which is able to have some probability at this point and some probability at this point will not have this probability at this point. Okay, so don't get confused with this. I said you in the last time that particle can move from this point to this point without touching this point. This is the normal in general confusion with the students. So I left you at this point. Now see, what we have plotted is the probability density. So in order to convert this probability density into probability, you need to get psi square d tau value, and in this case it will be more specifically psi square dx. So if you look at the finer picture of, say, a plot like this one, where it is touching at this point. Let me draw it again. It is like this one. and this is your point. Then draw a thin, think of this point. There will be one particular point at which the potential will be 0. At this point, psi is 0, okay, or psi square is 0. But what you need to find out is, probability. So it must include some volume element also. It will be psi square dx, and dx is a thin, very thin, draw it a thin space like this one. And if you expand this thin film, then it is like this one. And now you see, for this you have some non-zero space also, some dx value, okay. So non-zero space you will have to include in the dx value, and so psi square dx will show some probability even at node, very small, but some probability will be there, okay. So one thing. Another thing is that we in quantum mechanics, we don't talk about trajectory. So trajectory we don't talk about. So passing from this point to this point, question does not arise, okay. So this was the point where I left you, and this I wanted to clarify once again, okay. Now since we have done energy value also, so let us look at the energy value. Energy value was En is equal to n square h square divided by 8 ma square. So if I keep n is equal to 1 and I write E1 value, then E1 is equal to h square divided by 8 ma square. If I write n is equal to 2, then E2 is equal to 4 h square divided by 8 ma square. N is equal to 3, then E3 will be 9 h square divided by 8 ma square. N is equal to 4, E4 will be 16 h square divided by 8 ma square, okay. So if you look at the energy gap between any two energy level, in between 1 and 2, you can write delta E 1 2 with how much? Is 3h square divided by 8 ma square. In between 2 and 3, delta E 2 3 is equal to 5h square divided by 8 ma square. In between 3 and 4 is equal to 7h square divided by 8 ma square. So what you observe is that in each case, here you have 3, here you have 5, here you have 7. So if you plot an energy level diagram and you write n is equal to 1 here, then n is equal to 2 will be at this point, n is equal to 3 will be a slightly more gap, and then n is equal to 4 is equal to this one. So the gap here is smaller, the gap here is a little larger, even larger, and so on. Then if you draw n is equal to 5, it should be at this point. This will be the energy levels for particle in a one-dimensional box, okay. And now you see delta E we can write as h square divided by 8 ma square is common, and this will be equal to final minus initial square. This is the energy gap between the energy levels of particle in a one-dimensional box, okay. What you observe is that this delta E is inversely proportional to 1 by a square. So, if delta E is inversely proportional to inversely to dimension of the box. What does it mean? It means if you increase the size of the box, the energy gap will be smaller. And for a very large box, the energy gap will be so small that it will discrete energy level will vanish, and you will have a energy band. So, for larger box, quantization will go. Quantization goes, energy gap is small, energy gap delta E is small, is small, okay, and we have instead of energy discrete energy level, we have energy bands, okay. So, as long as there is discrete energy levels, the system can go from one energy level to another energy level by either absorbing energy or emitting energy, and that energy will be in the form of electromagnetic radiation, okay. Whenever this phenomena takes place, we say this forms the basis of spectroscopy. In all spectroscopy, we have a discrete energy levels, where by absorption of electromagnetic radiation, the system is transferred from one energy level to another energy level. So, this is valid for particle in a one-dimensional box also. So, if you write delta E is equal to h square divided by 8 m a square and nf square minus ni square, then you can write this delta E to be equal to h nu. So, this will be, since energy will be provided in the form of electromagnetic radiation, and this we can say hc by lambda is equal to h square divided by 8 ma square nf minus ni square, or 1 by lambda you can write as h divided by 8 ma square c nf square minus ni square, okay. So, this will be the wave number for a particular spectrum, or you can calculate the lambda wavelength also. Wavelength can be calculated, okay. So, energy level we have already drawn. Energy level we have already drawn. So, we say that is it possible for the system to migrate from this to this, from this to this, from this to this, and from this to this, or is it possible to come back from this to this, from this to this, or from this to this, or from this to this? Means, do we have any restriction or any kind of migration is possible? And so, we introduce the concept of which we will do in details in spectroscopy, but here just to introduce you that there are certain rules by which this transition takes place, and these rules are called selection rules. This selection rule is based on transition moment integral. So, we concept of transition moment integral, which we say is equal to, in between any two, say, psi 1, this should not be equal to 0. And if it is so, then if this is not equal to 0, then transition between psi 1 and psi 2 is possible. Psi 1 and psi 2 transition is possible. So the transition moment integral, and this I am sure we have done already. Psi 2 is the bra, and this is essentially psi 2 star. Here we have the real wave functions, we do not have I part, okay, and then where mu is, this mu is dipole moment operator. Dipole moment operator, which is nothing but multiplying by the dipole moment value, and the dipole moment mu is x into charges, whatever charge you have, charge q into x, okay. So charge into distance between the two poles is the dipole moment, okay. Now when it will not be, for this integral, to be not equal to, not equal to 0, the integrand should be symmetric to the center of inversion. What does it mean? Means if I show this integral as I, then I on inversion should not be equal to minus I. This should not be, okay. Rather I on inversion should be equal to I for I to be I not equal to 0. This should be the case, okay. Let us see what does it means. How do you invert this one? If you have this transition moment integral as psi 2 mu psi 1 like this one, then mu is actually, if I write x, sorry, psi 1 is equal to 0. So x is essentially, if you invert this one, it will go to minus x. On inversion, it will become minus x, okay. What about psi 2 and psi 1? So you should know the psi 2 and psi 1 symmetric properties you should know. And if you draw again, just two I am going to draw. Here you have positive sign, positive and negative. If you invert psi 2, then this will become negative and this will become positive. So inverted, so it will change sign. This will become negative, this will become positive. If you invert this one, there is no change in the sign with respect to the center of symmetry. With respect to the center, if you invert this one, then there is no change in the sign, okay. If you have the third energy level, then also the center is here. center is at this point. So again this is symmetric. So this is symmetric, this is antisymmetric, and this is again symmetric. So one level is symmetric, another is antisymmetric, then this will go on. Okay. If that is so, then if psi 2 is symmetric, psi 1 is also symmetric, and your x is antisymmetric always, then what will happen to the integrand? Integrand means psi 2 x psi 1 d tau or bra psi 2 x psi 1 ket. Okay. Then what will happen? If you invert this one on inversion, there will be no change in the sign of psi 2. Psi 2 will remain as such, but there will be a change in the sign of x, and psi 1 will also not change. It means I goes to minus I, and this is possible only when I is 0. Okay. So now you see the condition, the second one, I2 psi 2 is symmetric, psi 1 is antisymmetric, and x is always antisymmetric. So what will happen to the integrand? Psi 2 is symmetric. So first write this one and then see what about after inversion. After inversion, psi 2 is symmetric, so psi 2 will remain as such. X is antisymmetric, so this will become minus x, and then psi 1 is also antisymmetric, so this will be minus psi 1. And as a result of this, you will have psi 2 x psi 1. Means I is remains equal to, after inversion, remains equal to I. It means in this situation I is not equal to 0. So the transition is possible between two levels only when one of the level is symmetric and another level is antisymmetric. Okay. Because since then only the transition moment integral is not equal to 0. That is the condition for, and what does it means? It means what kind of transition is possible? If you look at the energy levels, one and two, one is symmetric, another is antisymmetric, it is possible. Okay. So this is symmetric, this is antisymmetric, this is symmetric, this is antisymmetric, this is symmetric. N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4, N is equal to 5. Okay. Now from symmetric to symmetric it will not go, so it will go to this one. Okay. What else? Can this go to this one? No, it will not go. But this can go to this one, and this can go to this one. So all these, because this is antisymmetric, this is symmetric. So all these transitions are allowed transitions. But transition from this to this, one symmetric to antisymmetric, is not allowed. Transition from this to this, is not allowed. Okay. What does it mean? If you look at this one, NF minus NI is how much? 1. If you look at this one, at this transition, what is NF minus NI? 4 minus 1 is 3. We say that transition will take place only when delta N is 1, 3, 5 and so on. and this is what is called selection rule for transition in between energy levels of one-dimensional box. Okay, this is how transition can take place in between two energy levels in particularly in a one-dimensional box. My pardon for my bad handwriting, but I hope you understand. You will understand, and you can learn these things. But anyway, once you have this one, then what does it mean? What is the application of particle in a one-dimensional box? Let's suppose if you have, say, a molecule like this one. In this particular molecule, you have four. This is what? This is butadiene. So, two double bonds you have. It means 4 pi electrons are present. And it's a linear molecule. Molecule can move along one diagonal. So, these electrons can move 4 pi electrons moving in one dimension. So, we can compare the spectra obtained from the transition of this molecule. If I draw the energy level diagram like this one, we have 2 electrons here, 2 electrons here, okay. Then the transition from this to this will give you some particular wavelengths, lambda max will be required for this transition. Means we do have the experimental wave. We know the if you know the dimension of the molecule, dimension of molecule means in angstrom or in nanometer, you know the size of the molecule, then simply delta E, which is h nu, which is hc by lambda, we have calculated as h square divided by 8 ma square and nf square minus ni square. So, you can calculate the lambda value, lambda calculated you can obtain from this equation, and this lambda calculated can be verified by experimental values also. Okay. So, for all conjugated dienes, it is possible to verify, to calculate lambda value and to find out what is the experimental value. And if I give you some value, let us see, number of double bonds, and lambda calculated and lambda experimental. Let us see, if you have 2 double bonds, then lambda max experimental is 217 nanometer and lambda max calculated is 205 nanometer. If you have 3 double bonds, then you have 329 is the calculated value and the experimental value is 259. If you have 4 double bonds, then you have 455 is the calculated value and the actual value is 304. If you go for a large molecule having 11 double bonds, then you have calculated value is 1344 nanometer and the experimental value is 452 nanometer. So, what do you see here? As dimension increases, the calculated value, lambda calculated departs from experimental value largely to a large extent. And I said you that if you increase the dimension, then dimensionality leads to departure from the quantum mechanical results. Okay, and instead of discreteness is also lost for a larger system, and you get a band structure like this one. Okay, even though it departs, but it gives you a good idea how to calculate the lambda max value for a conjugated dienes, and you will learn in organic chemistry about the conjugated dienes in more details. We will not talk about here. We can calculate the value from empirical calculations also. We can do this anyway. So this is what we this is how a particle in a one-dimensional box can be applied to conjugated diene molecules. Okay, so it's up. I will give you some problems in the assignments in order to calculate these wavelength for conjugated dienes, and then you will see this value is not the exact value. Where this you can find some departure in the books. This is approximately I am writing. Experimental value is approximately, because some books will report some value and some other books will report some other value, but it will be near to the 217, 15 like this one. Okay, so experimental value is very near to this one, and the calculated value is this one. And you see that if the system becomes large, the percent error is very high. So the result is if you apply particle in a one-dimensional box to conjugated dienes, you can say that the results are in very good agreement for smaller systems like diene and trienes, but for larger double system for several double bonds of conjugated dienes, there is the results is very unsatisfactory also. Okay. So what we learned from applying Schrodinger wave equation to particle in a one-dimensional box is one lesson is that we can solve the Schrodinger wave equations through the mathematically. So we say that 1D box problem, 1D box can be solved perfectly. So mathematically solvable. We can solve this one. Then the second point is that if you compare with the free particle, the quantization in the energy levels of 1D box results from the boundary condition. So quantization is a result of boundary condition. Okay. Then the third thing is that we have energy levels or better to say quantum state. Each quantum state has n-1 nodes where the probability of finding the particle is negligible, very small. Okay, I said you that the probability density we plot and n-1 nodes. Nodes is the point where the probability density is 0. Okay, because this one. And then the results are the model system can be applied to the conjugated dienes very easily. Okay. Having done this, then we can go ahead, and if we have the wave function and the energy level, then we can apply the postulates which we have done, and we can get the expectation value or average value of different physical quantity. So let's calculate one of the expectation value or expectation value or average value of position. And how do we write this? We write this quantity in between an angular bracket delta x. And I said you in the fourth postulate about the expectation value. Okay. And how do we determine what is the operator for position? Operator for position is simply multiplying by the position. So you write psi n, then you have operator for position, then psi n dx, and the limit is from 0 to a. So you can calculate this value, and if you do this, what you will write? You will write from 0 to a root 2 by a sin n pi x upon a, then you multiply by x, and then root 2 by a sin n pi x upon a into dx. This will be the expectation value. So it will be 2 divided by a, 0 to a, and then you have x sin square n pi x upon a into dx. Okay. The usual way of doing this calculation is that you convert this sin square n pi x into cos 2 n pi x. Let us say 2 divided by a, 1 by 2, 0 to a, and then you x into 1 minus cos 2 n pi x upon a into dx. Okay, 1 by 2 I have brought it here. Okay, so this you can write as 1 by a. I am writing every step because I don't know who is looking at these modules, so I am writing all the steps. So this you can write as x minus x into cos 2 n pi x upon a into dx. Okay, so this will be 1 by a, and then you will have one integral will be 0 to a x dx, and another integral will be 0 to a x cos 2 n pi x upon a into dx. Okay. So this will be, the first part will be x square divided by 2, and if you put the value of a, then it will be this one. This is your, this you will have to do by using integration by part. Okay, and if you do it, you will find that this comes out to be 0, and so the value becomes equal to a divided by 2. So the average value of the position is a divided by 2. Okay, this we can do. If you calculate the average value of the momentum, x component of the momentum, what you will get? Let us try to do this. So this will be equal to sine and the okay into dx. Okay, and so px will be equal to 2 divided by a h cross you can bring outside, and ddx of and so you can write at sine n pi x upon a cos n pi x upon a into dx. Okay, and this integral will be equal to 0, so that you have this one. Another thing which I forgot to tell you is that when we have written the energy equation, which is n square h square divided by 8m square. What is the minimum value of n? N is minimum value is 1, 2, 3 and 4. The minimum value is 1. So the minimum energy which is possible for this system is E1 is h square divided by 8ma square, and this is called in 0 point energy. If you have this much of energy, then the energy is there, so particle is not at rest. Even at minimum energy, particle is not at rest. So if you compare this result with this result, it is quite contradictory, because what you get is average value of the momentum, you get 0, and you say particle is not at rest. So if the particle is moving, there should be momentum. Okay. The answer to the question I did earlier itself, that you can express, if you look at this previous lecture, you will find that one of the solution was a exponential ikx, another was b exponential minus ikx. And when I talked about that, if you put b is equal to 0, your psi will become equal to a exponential ikx, and if you put a is equal to 0, then psi will be equal to b exponential minus ikx, and both will represent momentum in positive and negative direction, so that in one case the particle is moving in this direction, and in another case the particle is moving in this direction. So what this angular bracket expectation value tells you, that out of so many measurements of position, some will be on the positive side, so many measurement of the momentum, some will be on the positive momentum and some will be negative momentum, and the average will be equal to 0. So this does not tells you, this doesn't mean that potential itself is 0. Average value of position momentum is 0. Okay. So this way we can find out the average value of the physical variables of particle in a one-dimensional box. Okay. Now if you so another concept which we learned is 0 point energy and average value of position is a by 2 and average value of momentum is 0. Okay. Having done this, you can go ahead and calculate several other properties also. If I extend the concept of particle in a one-dimensional box, we can go for a two-dimensional box also. So if you go for a 2D box, what will happen? Means particle is free to move on a surface. 2D means it is a surface. So instead of x-axis, now you have y-axis also. So you will have two solutions for psi n. One will be root 2 by a sin n pi x upon a, and another will be root 2 by a sin n pi y upon a. Okay. What I have taken is a here also and a here also. So it is a square plane is a square plane. Okay. For our convenience, this n is along x direction, so you can put it nx also, and this n is ny, so you can put it ny also. So here you have nx and ny as the quantum number. Okay, two quantum numbers you have, and again the value will remain same. So the total wave function psi should be multiple of this one, psi n and psi n prime, psi n and psi n prime. So it will be 2 divided by a sin n pi x upon a and sin n nx, if you write nx ny pi y divided by a. So, this will be your total wave function. What about the energy? Energy will be nx square h square divided by 8ma square. And what about the energy of this one? This will be ny square h square divided by 8m a square. So, the total energy we can write as h square divided by 8ma square and x square plus ny square, where nx and ny is what? Nx can be 1, 2, 3, 4, ny also could be 1, 2, 3, 4, all integer value. The solution will remain same, except one thing, that's separation of variables, which you will have to do, and this I will tell you in details in part when we go for particular 3-dimensional box. So, I am skipping that part here in 2D box, okay. But the solution is this one. So, if you put n is equal to 1, nx is equal to 1 and ny is equal to 1, you get a value equal to E11, and that is h square divided by 8ma square. If you put nx is equal to 1 and ny is equal to 2, then you get E12, and that will be, this will be 1 and this will be 2. So, 2 square will be 4, 4 plus 1 is 5, 5h square divided by 8ma square. What we can do is that you put nx is equal to 2 and ny is equal to 1, and you write energy level E21, and this is equal to 5h square divided by 8ma square, okay. So, again you look at these two values, both these values are same, but the quantum state is different. In this case you have nx1 and ny2, and here you have nx2 and ny2. So, for the first time in this course, we have come to a state where two quantum states are represented by one energy level, one energy value, and this concept is called concept of degeneracy. Concept of degeneracy. So, we have degenerate quantum state, okay. So, this way you can go for 2, 2 also. So, for nx is equal to 2 and ny is equal to 2, you have nx square plus ny square. So, energy will be level will be E22, and that will be 4 plus 4 8 h square divided by 8ma square. So, if you draw this one, h square, 5h square and then 8h square, then you have one level h square divided by 8ma square. Then you have two energy levels of the same energy, that is 5h square divided by 8ma square. Then again you have single energy levels of 8h square divided by 8ma square, and so on. So on, you can keep on doing this one, okay. So, this is for a square shaped 2-dimensional surface on which the particle is free to move. And it's a symmetrical surface, all sides of the squares are same. If you go from this one to a different side, when A and B are different, it's also a planar surface, but now it is a rectangular surface. In this rectangular surface, you have A here and you have B here. So, let me write the other way around, that will be more easier for me. This is A on x axis, on y axis you have B, okay. Now, how will you write the Schrodinger wave equation, the solution of this particular model system? The solution will be 2 psi n you will write, and it will be done exactly the same way, root 2 by a sine nx pi x divided by a, and another sine nx you write and sine ny you write as root 2 by b sine ny pi b divided by a. So, the total wave function will be 2 divided by a sine nx pi x divided by a and sine ny pi b divided by, oh sorry pen, this will be y divided by b. So, this will be ny pi y divided by b. Okay. So, this will be the total wave function. What about the energy value? The same way, the energy value also we can write En is equal to what? Nx square h square divided by 8m a square and plus ny square h square divided by 8m b square. Okay. Also, now h square divided by 8m you can bring outside, but you will have nx square divided by a square plus ny square divided by b square. Okay. If you look at the energy levels and you put nx is equal to 1 and ny is equal to 1, okay, for this system where a and b is constant, this will give you only one energy level, okay, 1 by a square plus 1 by b square. But if you put nx is equal to 1 and ny is equal to 2, you will get two different values. In this case, and if you ny is equal to 1 and nx is equal to 1, sorry, this is equal to 2, this is equal to 1. So, if you make ny is equal to 2 and nx is equal to 1, then the two energy levels are not same. Degeneracy is lifted. So, we say is lifted. So, what happened? From the square system to a rectangular system, this energy level which was degenerate, here the degeneracy is lifted. The degeneracy is lifted. It means the two energy levels do not have the same energy value. Okay. So, what does it mean? From a symmetrical system to you went to an unsymmetrical system and the degeneracy is lifted. Okay. So, we can say that symmetry and degeneracy is very closely related. And if you remember correctly, then this you already have done in your inorganic chemistry, coordination chemistry, that the 5D or vitals, which is of equivalent energy, when you put it into an octahedral field or a tetrahedral field, the degeneracy is lifted and it splits into two different set of orbitals, T2G set of orbitals and EG set of orbitals. And if you go for further distortion of the field through John-Taylor distortion, then further splitting takes place, further degeneracy is lifted. Okay. So, this symmetry and degeneracy is very closely related. This also is a lesson from this particular particle in a one dimension and two dimensional box model. Okay. So, extending the concept of this particle in a one dimension and two dimensional box, we will go ahead and we will talk about particle in a three dimensional box in the next module. Okay, thank you.